Okay, welcome back everyone. IMR CDT Lecture 8, Rotations. What we'll be doing today is setting the foundation for two things, chiefly. One is solid-state NMR and EPR spectroscopy, where we'll have to rotate spin systems in order to perform powder averages. The other is for relaxation theory, where, as we'll see, the rotation treatments that we derive today will help us a lot in applications of relaxation theory, because doing, in particular, Redfield theory with just the school textbook rotations, sines and cosines, proves to be impossible. So we need to analyze today in quite some detail SO3, the three-dimensional rotation group, derive its irreducible representations, arrive at Wigner matrices, arrive at various general expressions like the rotational decomposition of various Hamiltonians, and put it together into a common framework which would provide perhaps the most general rotation infrastructure that we would in practice ever require. But starting with simple and fundamental things, let's take a look at a physical system, just a system here with a wave function psi that is positioned somewhere in space. And we shall assume that the space is uniform, so it's the same in every point, and that the space is isotropic, that is, all directions in that space are the same. That would only be the case if we are in an isolated system that's not in any externally imposed field or perturbation, because that would break such symmetries. So say we've positioned the system somewhere in intergalactic space, away from sources of all such permutations, and let's take a look at its energy. One thing that we would easily observe, and it stands to reason that it should be so, is that an overall translation of this system to a different point in space should not change its energy. Similarly, a rotation of the system, so if we turn it around, should also leave the system energy invariant. That is to say, in quantum mechanical language, what we have is, if originally we had this expression for the energy, that was E, where psi is our wave function and h is the Hamiltonian, then this expression should remain invariant under any such transformations. Now, if we take a wave function psi and apply a rotation to it, what we would have is a rotation operator times psi, and if we were to apply a translation to it, it would be some translation operator, t acting on psi. So what we must have, by our assumption of isotropic and uniform space, is that the expectation value for this Hamiltonian should not change. And so if we conjugate transpose this, so R psi conjugate transpose, we'll get this psi R conjugate transpose, so it just inverts. Same applies for the translation, and so if we reform that expectation expression, so it will be psi R conjugate transpose H R operator psi, this should be equal to the original H psi. And similarly for translations, so psi T conjugate transpose H T psi should be psi H psi. But this must be true for any wave function possible. And therefore, this must be true for the operators in general. And so what we conclude from here is that for rotations, R conjugate transpose H R must be H, and T conjugate transpose H T must also be H. Now, an important thing about rotations and translations is that they are unitary operators. Yes, they preserve the total probability, they preserve angles, they preserve distances. And so for unitary operators, what we can observe is that R conjugate transpose is the same as R minus 1. And similarly, T conjugate transpose is the same as T minus 1. And so this then transforms into this. RHR operators equals H, and then T minus 1 HT equals H. Well, if I multiply this by R on either side and this by T on either side, what I then get is H R minus R H equals 0. I just moved this term to the left-hand side, and then H T minus T H equals 0, and that is, of course, commutators. So we conclude that H commutator R is 0, and then H commutator T is 0. In other words, what we conclude here is that the operators, two of them independently, commute with the Hamiltonian. Now, this has implications for the expectation values. Those of you who did quantum mechanics in some detail will probably remember that this amounts to a conservation law, but let me just demonstrate this. So if we look at the expectation value of that operator, we will not at the moment elaborate on what it is, just the expectation value of this kind, so psi r psi, that would be psi r psi. And what I am interested in is the time derivative, so d by dt of this, and that would be d by dt of that. And well, let's just use the product rule. So what we've got is d by dt psi times r times psi, plus the middle term is 0 because r in our case is time independent. So what we've got as the second term in here is psi r d by dt psi. Well, this of course is the Schrödinger equation, so d by dt psi is minus ih psi, and this is also the Schrödinger equation conjugate transpose. And what we therefore get in here is I psi h r psi, then minus psi r, there's an I in here, h psi, so that's it. And when we take this psi out of the bracket this way and this psi out of the bracket that way, what we are arriving at is the following: psi, then I h commutator r psi, and that is of course 0 because we've just proved that this commutator is 0. So this is telling us that the corresponding observable, and we'll see in about 15 minutes what that observable is conserved. And the only assumptions that we ever made in the derivation here is that the space in this case is isotropic, and in the case of T, that this is uniform, it's the same at every point. Now let's find out what those operators actually are. So far we had them in an anonymous way, they were just R and T. Let's derive something specific. Let's derive an operator for rotation in the xy plane. So x, y plane rotation. Well, as we know from school, if we have a rotation operator by an angle phi in the xy plane, it maps x into x cosine phi minus y sine phi. it maps y, r phi mapping y into y cosine phi plus x sine phi, and it leaves z unchanged, so r phi acting on z remains the same. Okay, so let us now act with that rotation on a wave function. So r rotating by an angle phi in the xy plane, sine of x, y, z will give us psi of these things here. So x cosine phi minus y sine phi, y cosine phi plus x sine phi, and z. Let us now specifically look at very small rotations. So we will assume that phi is small, infinitesimally small in the differential sense. And then what we can do is we can look at a Taylor series for this around phi equals 0. So r of phi psi x, y, z, but we will be looking at a Taylor series of this, so r of 0 psi x, y, z plus d by d phi r of phi psi x, y, z evaluated at phi equals 0 times phi plus the terms which are of the order of phi squared. Yeah, the standard Taylor series. So this is clear. This is just our original unchanged function because r0 is a zero rotation and therefore an identity operator. Whereas this is here, and let us now differentiate it with respect to phi and put phi to 0 to see what's going to fall out. Okay, so d by d phi of this entire expression here. So what we've got is psi of x cosine phi minus y sine phi, comma, y cosine phi plus x sine phi, and z. Well, simple composite differentiation rule, so we get d psi by d first argument by d phi, d psi by d second argument by d phi, and so on. So what we're getting here is the following. So d by dx of, let's put it x prime, psi of x prime, y prime, z prime, where x, y, z prime are just these, and then times dx prime by d phi plus d by dy prime psi x prime, y prime, z prime, dy prime by d phi plus 0 because the z coordinate is just unchanged under rotation. So getting this expanded, d by dx prime psi x prime, y prime, z prime times dx by d phi, and all of this incidentally should be at phi 0. This is our x prime. Dx prime by d phi would give us x sine phi minus y cosine phi. This would disappear at phi equals 0. This would survive, and cosine would become 1. So this is minus 1. Then that term plus d by prime psi of x prime, y prime, z prime. Shouldn't forget that this all should be at phi equals 0. Here we already put phi to 0, so at phi equals 0. And dy prime by d phi. So d this by d phi is y sine phi with a minus, plus x cosine phi. This would go to 0 when we put phi to 0. This will survive. So this is just x. And finally, what we will observe is that when we put phi to 0 here, then x prime is equal to x because there's no transformation. So finally, what we get is minus y d by dx psi plus x d by dy. Should really be curly brackets in here and curly d's, partial derivative of psi. And when we take psi out of this bracket, we will see something really quite familiar. It's x d by dy minus y d by dx psi. Who recognizes the expression? The angular momentum operator, of course. And what we see is we had this, and we now get this under the infinitesimal rotation. And so finally r of d phi, so we'll just explicitly make it infinitesimal, is r 0, so we'll apply it to wave function here of psi, plus this thing here. And if you remember the expression for the angular momentum operator, it had an I in front. More specifically, this is minus I Lz, so the angular momentum operator around the z-axis. So this plus here becomes a minus. Minus I Lz operator acting on psi phi, and because we chose d phi here, that's d phi plus something of the order of d phi squared, which we can ignore. And therefore, because the wave function here is arbitrary, we arrive at the following expression for the infinitesimal rotation. So r d phi is 1, yeah, this is just a unit operator, minus I Lz phi and d phi. So we derived an interesting thing. It turns out that the angular momentum operators actually accomplish infinitesimal rotations. And it is they that get conserved as a result of the isotropic nature of space. You see, we've proven something really fundamental. The only thing that we ever assumed was that space is the same in every direction. And 2 boards of mathematics later, we suddenly derive the law for the conservation of angular momentum. We could have done the same for the translation, in which case the linear momentum would have popped out. Or, interestingly, we could have done something for the same for the time translation. It's a simple fact that if we do the experiment tomorrow, the energies of the system, assuming it's prepared identically, would be the same. And this time translation invariance would then have left to the conservation of energy. So the 3 fundamental conservation laws that there are in the universe are sole consequences of the 3 basic symmetries of that universe. That space is uniform, isotropic, and that time in it flows uniformly. If time wasn't uniform, there would have been no conservation of energy. And this is, however general, is still a special case of something even more fundamental. The theorem has been proven by M. Minota in 1915, that any differentiable symmetry of the system, and you remember that differential symmetries were governed by Lie groups, corresponds to a conservation law. So anything that we can do to the system in a smooth way that leaves the system Hamiltonian unchanged, its generator, so the corresponding infinitesimal transformation, would correspond to a conserved quantity. Okay, we derived the infinitesimal rotation, so let us now look at a finite rotation by some arbitrary angle phi. What we'll do is consider the following. R of phi plus d phi, so it's a rotation by an angle phi, and then by a little bit next to it, which for a rotation around just a single axis, it's a commutative group. So what we can do is say the following: R d phi applied to R of phi. For a group of rotations around a single axis, this is always the case. And that, as we just derived, is 1 minus I Lz d phi acting on R of phi. So why don't we open the brackets? We get R phi minus I Lz R phi d phi. So what I'll do is I'll take this over to the left-hand side, and I'll divide the whole expression by d phi. So what I'll get out of it would be R of phi plus d phi minus R of phi divided by d phi equals minus I Lz R of phi. And these are all, of course, operators. Well, this, in the limit of infinitesimally small d phi, is actually a derivative. So once we take that limit, we get d by d phi R of phi, and that is minus I Lz R of phi. Well, this is actually the equation that we know extremely well how to solve. We did it so many times that you probably remember the answer. The way this is solved is that R of phi is exp minus I Lz phi, the exponential of this operator here, times R of 0. But R of 0 is just a unit matrix, so we can simply remove it from here. And this, therefore, is our expression for the finite rotation. It's just an exponential of the Lz angular momentum operator. And this is for rotation in the xy plane. And similarly, if we repeat the derivation for the rotations in the zx and the yz planes, we get Ly and Lx in the corresponding expressions. So therefore, an arbitrary rotation by first an angle gamma around, say, z, then by an angle beta around y, and by an angle alpha around x, would be written down like that. So R of alpha, beta, gamma, where these are not yet Euler angles, not necessarily, would be. Now, we need to be careful about which order we apply operators. You know that the first operator to be applied is the one that's nearest to the function. And so if we are rotating first by an angle gamma in the xy plane, so we should have an exponential here, e minus I Lz gamma, and then an exponential e minus I Ly beta, and then an exponential minus I Lx alpha. So these are three sequential rotations, first by gamma around z, then by beta around y, then by alpha around x. And you see, this casts our angular momentum theory in a very peculiar light. The reason why these operators were so central to it is that they are actually infinitesimal rotation operators. And you would recognize the sort of things that we had in the Lie groups in the previous lecture. These are exponentials of I times Hermitian operators. So these are unitary transformations, and they contain an operator and a parameter. So let's say the group of rotations around Z would be a uniparametric Lie group with the generator Lz and a parameter gamma. And because we've got three axes in the three-dimensional space, and any rotation can be decomposed in this way, the group of rotations is a triparametric Lie group. And these, of course, we all remember. Lx is minus I y d by dz minus z d by dy. Ly is minus I z d by dx minus x d by dz. And finally Lz, which we actually derived today, is minus I x d by dy minus y d by dx. And we also should remember from the previous lecture that every Lie algebra, this is where these operators live, and it is mapped onto a Lie group by the exponential map, that they have structure relations. And so our famous commutators, just as we had them for Pauli matrices, which was the basis of SU2, these are the basis of SO3. Lx, Ly is I, Lz, and so on. These are actually structure relations of the algebra corresponding to the Lie group of all three-dimensional rotations. And the central role that these commutators play in the theory of angular momentum is down to the fact that they are the infinitesimal generators of the corresponding group. Which brings us to the actual group. So meet the SO3. SO3, strictly speaking SO3R, because the angles are necessarily real, the group of rotations in three-dimensional space. It has three generators, Lx, Ly, Lz, whose linear combinations under the exponential map generate the group. So this is the algebra, SO3 small, and this is the group where exponentials live, things like x minus I, Lz, phi, so SO3. Incidentally, this explains the term rotating frame. We now know that this is a rotation, and as you'll see an awful lot in magnetic resonance, it's the transformations of this type that actually correspond to putting the system into a rotating frame. Some operators here. Before we proceed, however, we need to make one further adjustment, and that one is purely physics motivated. That is to do with the fact that we actually don't just have Lx, Ly, Lz, and Z commutators in physical reality. What we also have is operators like that. L plus is Lx plus I, Ly, and things like L squared, which is the total momentum operator, which is Lx squared plus Y squared plus Lz squared. Now, this presents a problem because, as you remember from the previous lecture, in SO3R, in the corresponding algebra, only real coefficients were allowed in the linear combinations, and we've got an I here. Furthermore, we only had the Lie bracket. We didn't have an actual product defined in a Lie algebra, which means the square is technically speaking outside. So we need to extend this a little bit. What we need to allow is two things. We need to allow complex coefficients to have this, and we need to allow powers of generators in order to have the L squared. Now, I'm simplifying here somewhat, but the result of allowing these things, the resulting object is called the universal enveloping algebra. So if we take this SO3 and we allow, first of all, products and then imaginary and complex coefficients in general, we arrive at U of SO3, where it's no longer just the Lie bracket, so we do now have an associative product there as well, which allows these things. Now, this USO3 generates a bigger group under the exponential map, so clearly we should go back before we go into the SO3R, which is unitary. The exponential map of this would not necessarily generate unitary operators because of this I in here, but it's clear that we are in practice, when we are doing physics, actually working inside the envelope of SO3 rather than the vanilla SO3 Lie algebra. Now, there's another term that I would like to introduce, is a special name that mathematicians have got for such things. The sum of squares of all the generators is called the Casimir operator. And its property is one of quite useful properties that it has, is any of its irreducible representations is proportional to a unit matrix. And, well, as we know, that's actually the case. I mean, L acting on any specific angular momentum state just returns that state times the actual angular momentum times angular momentum plus 1. So it's not sensitive to the projection quantum number. And so its representation on the space of states with a given primary quantum number would indeed be proportional to the unit matrix. But we'll get to that in due time. So this is called the Casimir operator for the SO3 Lie algebra. Okay, now that we understand the algebra and the group theory of rotations, it's time to go through a fairly boring list of historical conventions for rotation specification. I will not write them out on the board. This would simply just amount to copying your handout. You have details for two Euler angle conventions, for angle axis parameterization, for quaternions, and for the directional cosine matrix in your handout. I'll give you a couple of cautionary notes in here. On the surface of it, the Euler angle convention is the easiest one to understand, but there be dragons. The problem with Euler angles is that the three generators that they have, I've given them to you in the equation 13, do not commute in the correct way. If you look at the convention, the one that uses the stationary coordinate system, it's first a rotation around z, then a rotation around y, and then another rotation around z. The first and the third generators commute. Now, for a valid parameterization of a Lie algebra, the requirement is that they do not commute. And that's clearly broken. The practical result for that is it's rather straightforward to translate from Euler angles into any other parameterization, or from Euler angles into a quantum mechanical calculation of your system. But it is rather difficult to effect the reverse translation from any other parameterization into Euler angles. There are nasty singularities. The differential equations for three-dimensional dynamics in Euler angles are not well behaved. And in fact, over the years, various space agencies have lost a few satellites because something failed in that exact mathematics, and they could not maintain the necessary attitude in space, so that the solar panels would point towards the sun, for example. So there's a history of problems with Euler angles. So things like our spinach library, they never store anything inside them in Euler angles. They translate them into DCM or into spherical tensor notation, which we'll get to in a moment. So please be careful. And if somebody asks you to extract the Euler angles out of some experimental data, either tell them that that is a problematic transformation, or be prepared to get utterly lost in the relevant mathematics. There are a couple of review papers in the literature, one in particular by David Simonovich, explaining this in greater detail, but the bottom line is don't use Euler angles unless you absolutely have to. Angle axis parameterization is a lot better in practical simulations, and really, to be absolutely safe, you should be storing all interactions as spherical tensor coefficients. Which brings us to the next topic, the representation theory of the rotation group. So what we now need to do is to build the matrices and the rotation infrastructure for all of these things. The reason why we need to build those matrices is these are differential operators. Computers don't like them. Furthermore, if we do try to make them into matrices, these things are rotating functions. The Hilbert space of all well-behaved functions is infinite dimensional. So any faithful representation of these operators is going to be infinite dimensional as well. And so we need to find a reduction. So we need to block up those matrices into some finite blocks, which would be irreducible representations of the group, and then we can use them. Now it turns out such blocks do exist, and because of this exponential map relationship between the algebra and the group, and the fact that the exponential map preserves the block structure of the matrix, in order to block out the entire group, what we need to do is we need to simultaneously block diagonalize the three generators. Then the group would be block diagonalized automatically, because this is just the exponential linear combinations. Simpler still, we know that Lx, Ly, and Lz all commute with the Casimir operator here, and I wouldn't prove this statement, it should have been proved in your basic quantum mechanics course, but the commuting operators share invariant subspaces. So therefore, whatever block diagonalizes L squared would automatically block diagonalize Lx, Ly, and Lz. So we now need to block diagonalize L squared, or maybe, if we could, actually diagonalize it outright. Let's try. We have L squared, which is Lx, Ly, and Lz, times some functions. Psi would be some number, A, times psi. So the standard eigenvalue and eigenfunction problem for a quantum mechanical operator. Now, this is not an angular momentum course. Most of you had an angular momentum course in your life anyway, and you probably remember what these functions are. I would not derive them. It's a significant amount of mathematics, much more significant than we've got the time to elaborate upon here. But the functions that have this property are known as spherical harmonics. The expressions given in your handout, it's fairly complicated for the harmonics themselves, but fortunately they do have fairly simple properties under the action of the various operators. In particular, all of you should know, if you don't, read it up in Atkins. L squared y Ln, the cardinal and the projection quantum number, they come out of the requirement for every rotation to be periodic, is L plus 1 y L. Then Lz acting on y Lm is m y m. And something that's not frequently given in textbooks, but the action by Lx and Ly also has a fairly simple form. Not as simple as this, but it's there. It's a half of root L plus 1 minus m plus 1 y L plus 1 plus another root L plus 1 minus L minus 1, should be minus here as well, y L minus 1 bracket. So you see, L squared is diagonal. L squared times a function is a constant times a function. Lz is diagonal, same story, but Lx and Ly, there's a similar expression in your handout for the Ly operator. They are not diagonal because they mix different ranks, but they are block diagonal because they only mix the m ranks. They leave the L ranks the same. And so what we achieved is we block diagonalized all operators. Some of them got diagonalized outright, which is also block by definition, and these into individual sub-matrices corresponding to just given values of L, the total momentum, and so on. And of course, under any multiplication operations that there are in the group, the block structure would be retained, and this can be shown to be the best possible such blocking. And so these matrices, this one would be 1 by 1, this one would be 3 by 3, this one would be 5 by 5, and so on, so 2L plus 1, are known as the irreducible representations of the rotation group, or in the trade, Wigner matrices. And we've done this in the basis of these spherical harmonics, the spherical Legendre polynomials. So now let's take a slightly closer look at the relationship between the Wigner matrices and the spherical harmonics. So we'll be looking at things like y, L, m, some rotation in here, and then y, L prime, m prime. As we saw already, the L ranks are not being mixed, and so if L is not equal to L prime, it's 0 anyway, so we can remove the prime from here. And the result is known in the trade as a Wigner function, m prime, which would depend on the three indices, and the same rotational parameterizations are, if this is alpha, beta, gamma, then the Wigner would depend on alpha, beta, and gamma. And the values for specific cases are given in your handout. There are huge tables in the literature. They can be expressed in very general terms through Legendre polynomials as functions of L, m prime, and the rotational parameters, and so on. Big books are written on the subject, so take a look. But let's see in particular how a given function, for example, a spherical harmonic, is rotated under such transformations. So what I'll do is I'll multiply both sides of this by YLM here, and I'll also stick a YLM here, and I will take a sum over the m index of both sides. So a sum here over m, and a sum here over m. Now, since we keep the L index static anyway, it's a given in our case, this is a unit matrix for a given value of L. So we can remove that, and what we therefore get is R, the rotation, applied to Y, L, M prime, is a sum over M, D, L, M, M prime, Y, L, M. This is a very important relation. What it says in simple terms is under a rotation, when we apply it to some function, spherical harmonics in particular are transformed in a very simple way. The L ranks are not changed, and the M ranks are mixed into a linear combination with coefficients given by the Wigner function. Now, this is a huge simplification, because remember, we are transforming functions. And if I had some complicated function of x, y, z, under a coordinate system rotation, what I would have is a complicated function of complicated trigonometric expressions. And then if I rotate it again, composition of rotations in 3 dimensions, as you know, is very complicated. There's lots of sines and cosines coming out. And so, say 3 rotations later, if we were to transform our functions the conventional way, using trigonometric relations, the mathematics would have exploded and killed even powerful computers. Whereas if we are rotating things in spherical harmonic basis sets with Wigner functions, the only things we get are just nested sums. This is really very simple. What it would also be helpful with later on, as we'll see, is relaxation theory, because that one does have complicated correlated rotations. And there, the orthogonality of both the y's, remember they are eigenfunctions, and are therefore orthogonal, because the operator whose eigenfunctions they are is Hermitian, but also d's. You remember it was 1 or 2 lectures ago that I've shown you the great orthogonality theorem for irreducible representations of operators. That these things are also orthogonal as functions. And so those orthogonalities, together with this linear combination relation, make rotations very, very simple. This is particularly acute in solid-state NMR, where you have an interaction that's positioned somehow in the molecular frame, but is then rotated into the crystal frame. The crystal is rotated relative to the powder, which is there in the spinner. The powder is in the spinner is rotated relative to the applied magnetic field, and so there are multiple nested rotations there, which are only possible to treat systematically using this. And so I'm preparing you to the next lecture where we'll be dealing with solid-state simulations. This is a very convenient way of rotating this. But you'd notice that, of course, we are rotating functions here, but in spin dynamics we have operators. And it turns out that it's possible to find a similarly simple expression for spin operators using the following trick. I've given you a big table in your handout. It gives you these spherical harmonics of zeros, first and second rank in terms of sines and cosines, just as spherical Legendre expressions, but also in terms of Cartesian coordinates. For example, if we look at y20 spherical harmonic, then its expression in terms of trigonometric functions is root 5 over 16 pi, the normalization, 3 cosine squared theta minus 1, where theta is the spherical angle, beta if we choose to use the Euler angles. But it also has a Cartesian coordinate expression, and the expression is the following. It's 5 over 16 pi 2z squared minus x squared minus y squared divided by r squared, where we can just choose to have a point on the unit sphere, in which case r disappears. Now, the trick is the following. In order to obtain the spin operators with the same rotational properties as the spherical harmonics, what we need to do is take a Cartesian coordinate expression for the spherical harmonic and replace z with Lz, x with Lx, and y with Ly. And so the expression here becomes a spin operator, and the operator thus obtained is known as irreducible spherical tensor operator. And they inherit these convenient rotation properties. Now, they have to be normalized in a slightly different way in order to commute as appropriate for generators of the algebras, but the expressions are given in your handout and in the table that I've provided to you. It's also oftentimes convenient to express x squared and y squared through the plus and minus operators, the raising and lowering ones. And so after all those transformations, what we obtain is the following: root 2/3 Lz squared minus L quarter L plus L minus plus L minus L plus. It is quite easy to convince yourself that when you replace the plus with its expressions y, x, and y, this translates to the expressions that we had for the x and the y in here. So this spin operator would inherit the convenient rotational properties of these spherical harmonics, just the Wigner functions as the coefficients. Now, you would notice that there are powers here. This would be a quadrupolar operator for spin 1, for example. There are corresponding two spin operators that have got the same rotational properties. The derivations are broadly along the similar lines in here. They are given to you in equation 23 in the handout. But the important thing is the spherical tensor operators under a rotation, so say R of alpha, beta, gamma, are rotated in exactly the same way with minor index permutations as the spherical harmonics. So what we've got in there is a sum over, let's just put a t in here. So R times an irreducible spherical tensor operator T L M. The L is conventionally just written above in brackets. That would be just the linear combination of the irreducible spherical tensors of the same rank, and the L ranks would not be mixed, the sum would only be over M. So from M prime minus L to L, the ranges are inherited from spherical harmonics. T, L, M prime, D, L, M prime, M of alpha, beta, gamma, where this could have been any other parameterization of the rotation group, not just the Euler angles. One particular thing about spin, you may remember it goes back to the interactions that we had in the Hamiltonians. There are only three types of spin interactions. There are the ones that are linear, there are those which are bilinear, and there are those which are quadratic. What it means in practice is we only ever have irreducible spherical tensors of L ranks which are smaller or equal to 2, because higher powers of this do not appear. You will need a cubic operator to have higher powers in here and so on. But in physics we only have pairwise interactions between particles. Various effective interactions are effectively quadratic. And so in practice the series in irreducible spherical tensors, which in principle could have contained an infinite number of L blocks, actually terminates at L equals 2. And so the most general expression for any spin interaction whatsoever is the following. If we have two spins, L times A, the interaction tensor, that's 3 by 3 matrix that we looked at in some detail already, S, so two spins interacting with one another. The biggest we can possibly have is A0, 0 times T. 0, 0. The isotropic part, which would have power 0 in all the coordinates and spin operators, plus a sum from M minus 1 to M equals to 1, A 1M, T 1M, plus a sum from M minus 2 to 2, A 2M, T 2M, spherical tensor operator. What is also the case is that the first rank contribution is often either extremely small or in practice unobservable. In fact, although it is known that these terms exist, I've yet to encounter a situation where they actually matter. And so typically in all practical calculations, this is also destroyed. As we know, the isotropic components of interactions which are here are rotationally invariant. Simply speaking, the L0, 0, 0 is just a constant. And so the only thing we in practice need to rotate is this. And the expressions for these numbers are tabulated in your handout. And you see how we simplified a problem of rotating a spin system. You would have quite a lot of these interactions, hundreds of them in some systems. Rotating them with sines and cosines repeatedly would be troublesome, but what we just need to do in this case is to translate them into these irreducible spherical tensor coefficients, and then they can be rotated with these Wigner matrices, which, although these expressions look formidable, are simply just numbers. And these numbers are provided either in the textbooks or in your handout, or if you download the Spinach library, there are open source functions in there that just give you the matrix of all these for a given set of indices and ranges of indices. There are also functions in there already programmed in that have all these coefficients in there, and you just call a function and give it this matrix, and it gives you the A00, the A2, all 5 of them, and if you do require them, also these ones, as well as returning you the corresponding operators. There's one particular equation that simplifies life considerably at the problem setup stage. The expression here becomes particularly simple when A is diagonal, so in its eigenframe, so to speak, and that is your equation 27. I think I wouldn't write it out on the board, but what you would recognize instantly in the coefficients are the isotropic part, the axiality, and the rhombicity of the corresponding interaction. And this is why I recommended those parameters when we dealt with the parameterization of spin interactions, because they occur naturally in the rotational decomposition that's based on the representation theory of the rotation group. Okay, so let's wipe the board and give one final ground recipe on how to rotate your spin systems. As I noted already, we'll ignore the antisymmetric components of Zeeman tensors for reasons of their practical inconsequentiality, and with that in place, a very general theorem. Any Hamiltonian in magnetic resonance at any orientation has the following form. H is H isotropic, the part that doesn't depend on the orientation, plus a sum over two indices, k and n from minus 2 to 2, d2km alpha beta gamma q km, where alpha, beta, and gamma are system orientation parameters, and q, km are 25 constant operators. Well, it's a pretty general statement. Let us now prove it. In particular, let's derive the expressions for q, km. They are known in the trade as the rotational basis. So a Hamiltonian would contain the isotropic part, which we don't need to worry about because it doesn't rotate. But the parts that do rotate, the anisotropic parts of various interactions, would come in 3 flavors. Those would be the linear ones, the bilinear ones, and the quadratic ones. And so we need to therefore take 3 terms in here, and we also need to make sure that they are rotated into the correct place. So what we have is some rotation, and we'll be working with super operators here because it's a rotation of an operator. That will be a sum over all spins in the system. Note the capital L, it's not a small l, this runs over the spins. Then a sum over m minus 2 to 2, a to m of L belonging to L's spin, then t to m of L. So this runs over all spins in the system, and this, as we saw, is the expression for the anisotropic part of, in this case, a Zeeman interaction, or a spin-orbit coupling to an external angular momentum, anything that only involves a spin once. Second term, similarly rotated, would involve bilinear interactions, dipolar coupling, hyperfine coupling, things like that. So what we'll have there is a double sum over L and S, with all the blah 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 about avoiding the double counting. So L runs over spins and S also runs over spins. So then a similar sum, and you will now see the power of the rotation arguments that we derive, because they look essentially the same no matter what the interaction is. So a sum from m minus 2 to 2, a m to different a's, they now depend on L and S, then t to m of Ls, the two spin irreducible spherical tensor operators. You see a very similar expression, even though the interaction type is rather different. Plus the last thing that we have in our NMR and EPR systems are quadratic interactions, zero field splitting in case of EPR, and quadrupolar coupling in the case of NMR. So similarly rotated, a sum over spins, a sum over m minus 2 to 2, a to m, and to differentiate them from this and that, I'll just call it S to S, so the interaction split with itself, as it effectively happens, then T to M, S, and S. Okay, let us now pull in this rotation and use that Wigner function expression for those rotations. So I'll take this R, I'll move it all the way here, and I will replace R acting on T with a sum with Wigner function coefficients of T's of the same rank over M. It will be a bit of a long expression, this one, but we'll persevere. So not forgetting the isotropic part of our Hamiltonian, which sits happily there because it's not affected by rotation. So a sum over L. Now we would have a sum over two indices, because this transforms under rotation into a linear combination. So we have a sum over k and m from minus 2 to 2, a m2 of L, t to k, see it's a different coefficient, and now we've got d to k m. So that's the linear combination and the sum over k. Plus the similar terms for the others. I do need to write them out explicitly. We'll be taking things out of the bracket next. A sum over k and m from minus 2 to 2, a to m L S, then t to k L S times d to km. And the last term, incorporating our quadratic interactions, would be a sum over S, a sum over k and m from minus 2 to 2, a m to s s, and then a similar linear combination that results from rotation, t to k, and then of s and s times d k m2. You'd notice that, well, first of all, the rotation has vanished because we now have explicitly applied it, but dkm occurs everywhere, and it's the same dkm, assuming our system is rigid. Let's pull it out of the bracket. What we'll get is h iso, and what I'll also do is I'll take the summation sign out of the bracket in the other direction, because it's the same summation sign in all cases. So we'll have a sum over k m from minus 2 to 2 of some horrible crocodile, and the crocodile is given to you in the handout, times dkm2. Well, that's exactly the form. You see, sum km minus 2 to 2, there we are. Wigner functions, 2 km, and we'll give the name to the crocodile, we'll call it qkm and the expressions are given in your handout. So we did actually prove, although we required an assumption that the system is rigid, otherwise these are different and we wouldn't be able to take them out of the bracket, but we did prove this statement in fullest generality. And this also provides the most straightforward way of rotating your systems. Once at the beginning of the calculation you are calculating these QKMs, and then every time you're actually applying a rotation to the system, the only thing that needs to be done is a different linear combination needs to be taken of those. Now, the importance of this cannot be emphasized enough. You see, as you saw already in the lectures that dealt with practical simulations, that is me typing on the screen and talking, these things were chronicle products of matrices. They are very expensive computationally. And if we were to reform the Hamiltonian at every single instance for every single orientation because it affects our interaction matrices, that would have been a long calculation. Now this has the advantage that these operators only need to be formed once. And then a linear combination is a very cheap procedure computationally, and so most of the time in an actual simulation would be spent in something productive, like propagating it forward in time if you're solving it in the time domain, or diagonalizing it if, God forbid, you're solving it in the frequency domain, but there goes. And so what we need, therefore, essentially, is these Q's, and the bigness and the isotropic part just goes on. So the recipe, the final recipe, is given to you at the very end of the handout, and this is how to rotate the system. Let's make a bit of space on this board. And this is how spin systems are rotated in all mainstream simulation packages. It could be Spin Dynamica, it could be Simpson, it could be Easy Spin, it could be Spinach. If you look under the bonnet, this is how rotations are always done. So, recipe. Item 1. Get all of your interactions into Cartesian 3x3 matrices. So, get all interactions into 3x3 matrix form. Item number 2. Translate these matrices into spherical tensor parameters. These ones. Can be done automatically if you download Spinach and use it. Spin Dynamic, I think, has got the facility as well. Other packages might be slightly harder, either because they're closed source or they're in Fortran. MATLAB and Mathematica does have a huge advantage of readability and usability out of the box. But anyway, so translate interaction parameters, matrices into A, L, M, and the spherical tensor coefficients. Number 3, compute H iso, just the isotropic parts of all interactions go in there, and QKM, using the equations supplied in the handout. Alternatively, if you are using Spinach, the Hamiltonian function just spits them out. So you can call it and you'll get those operators straight out of it. So number 4, use this equation, star, to make your Hamiltonian at any specific orientation. There we are. This is how it's done. One reason is convenience. The other reason is computational efficiency. And the third reason we will see in a couple of lectures from now when we deal with Redfield relaxation theory, because that one is also formulated in terms of correlation functions of Wigner functions, and therefore we will require this exact form in order to obtain the relaxation superoperator. Okay, that's it for today.